Hello everyone, this is Bradley. Today this is a renewed tutorial talking about this circuitry board animation I've done in the past. There were lots of requests of renew this tutorial because of changes in Blender geometry nodes and along with the change of my presets. However, I looked into my old tutorial and I find myself explaining the nature of many setup well enough. And many questions people asked about this setup is quite minor. So I'm not very convinced the benefit or necessity to renew this tutorial, because if you understand the setup, you should be able to replicate the end result nicely in the older tutorial. And it's predictable that there are going to be more changes in Blender itself, whether it's in 4.5 or 5.0, because right after 4.5, we're going to have big changes in 5.0. So I'm not sure if this tutorial will have another huge change that confuses people. In this case, I would say I'd recommend you to ask in the Discord server with your screenshot, or just try to understand the setup and think about that. So let's start. So here we're in Blender. The principle of this setup is quite straightforward, that you start with a kind of chip-like curves, because we're going to extrude these curves along its normal direction step by step. And during each extrusion, we're going to decide if we're going to turn this curve on left or on right, or just straight forward. So that over the case, there can be some rotation or turns. Another thing we're going to deal with is that when you're having a kind of a RayCast to detect if you're going to collide in the next move, then you stop moving in this kind of case. So this is detection. And we're going to repeat the same process to determine if there will be new branches generated for these kind of curves, and follow the previous instruction whether to turn or move forward, and so on and so forth. Okay. So this principle is not very difficult, but there will be lots of notes. As always, I'm going to use the presets, which you can download for free from the link in the description. I'm going to start with a plane to hold the geometry node tree. You can also use the plane edges to start with our chip-like structure. But since I need a kind of curve, there is a better method to just use this quadrilateral, which is giving this kind of square-like shape while it's outputting the curve. Right now, if you use a curve points preview, just for a kind of preview reason, you can actually see that there are only 4 points available. We're going to increase the amount of points using this resampling, the resample curve. So now we have 10 points. I'm going to set that to 20 points for the moment. Next, we need to think about how to extrude these curves. I'm going to use a preset called Append Point to Curves. This is basically an extrude mesh node on this kind of vertices. So for example, if you take a mesh line and you're extruding a mesh, let's take the offset into combine XYZ on the x-axis. Then you can see the starting and the end of point is extruded out with a new point attached to it. And this is basically comparable with our append point to curve. That if you start with a curve line, and you can take this combine XYZ, then you have the similar setup at the end, which is being selected in this case. So if we plug these append points to curves, then you can see the end result in this offset is that you have one point which has been extruded. Because for each curve, there is only either end or start being selected for this kind of extrusion or appending. So right now, what we need to do is to separate all these 20 points that we resampled into an individual curve for each. So there is a function which is called a curve point. And if you directly use that, you will find that it does not show anything in the viewport because we have very bad visualization of these kind of curves. That's why it will always be better if you visualize with these kind of curve points per view, that you will see the points are still there. It's just not visible as a kind of curve. And now if you switch these kind of curve points into our append point curves, you can see that each point is having kind of extrusion instead of only one extrusion. Right now we are offsetting everything on this 1, 0, 0 direction, but we want to make them aligning to their normal direction. So the north point should go to the north, east points goes to the east, south goes to the south, west goes to the west. So this is the normal direction. We're going to use a normal. Now, if we directly replace this normal with our combine XYZ, then you can see it's not really changing in the way we want. This is because we're having a kind of transform going from the curve into this kind of curve points, that this normal is not being preserved. So we need to capture this normal at this geometry status. So take and capture attribute. You take normals into that, and now if you switch that into the offset, then immediately you can see what we're getting is this kind of a structure. We are going to repeat this process a lot, many times. So we take a repeated zone so that there is running a kind of loop over and over again with the same operations. Let's put these append point to curves into this repeat zone and feed back in our geometry. If you look at the end, we still need to have our offset being done. So take this normal into the inputs and remember to output this normal to the output so that this information can go back in the next iteration. Right now, because this is running a loop that you extrude once and you go back to extrude twice, go back third time, fourth time, fifth time, so that if you increase the iteration, it will just keep growing in a kind of far distance. Okay, I'm going to expose this iteration in our group input so that we can just control this setup in our modifier panel without going back and forth in our large node tree later. And now we can remove all this kind of demonstration with mesh line, but just remember that this is essentially using our extrude mesh function for curves. Now we have our curves extruding in a linear consistent direction because we're using a constant normal. We can use a vector rotate to rotate this normal direction so that we are having a negative 45 degrees rotation or positive 45 degrees rotation. And we're going to set up a condition to rotate on each step of this extrusion. Here I'm going to use a noise texture so that for each point there will be a noise factor being generated. In a normalized condition, this noise texture will go from 0 to 1 roughly. And then I'm going to use a map range to remap this 0 to 1 to something else. I'm going to use the stepped linear and take the negative 45 to start with and the positive 45 to end with, and take the step size 2. So that I start with the negative 45 and the step 1 going to 0, and the step 2 will be positive 45. So this is what it means. Okay, and this is degrees, so we need to turn degrees into radians. This is actually a mass node operation, and you plug that into the angle. Right now, we do not see any changes. This is mostly due to parameter issues. You do not have a dense enough noise, and we also do not have enough iterations. So you can increase these iterations to kind of high number, and you have to really zoom out to see this entire structure. Here, I'm going to just scale down this entire setup with a value precision. So in this case, I'm going to scale that down to about 10% of its original value. Now you can see everything has been scaled down. You can increase more iterations, and there are more turns being generated due to our noise texture. And you can try to play around this value. Another issue is that if you looked into this noise texture, probably on a dense grid, I guess, then you will realize this factor is not 100% black and white. So sometimes it would be better if you turn down this roughness, or you may even color ramp it, so that to make it more darker or whiter. To make it kind of extreme so that it covers the range of 0 to 1 for this kind of rotation. So now if you replace this result, this will be what it looks like, and you can try to tweak this kind of value and try to manage the kind of settings you want. Here I'm also going to expose the amount of points that we resample at the most beginning, so that instead of having this many lines, where we can actually increase the count. And because they're using the same noise, so that they may potentially follow the same pattern because of this noise texture coordinate, and it may look interesting already even without all this kind of intersection prevention algorithm. And up to now, this is not really a complex setup. I hope you can actually understand the concept behind all these kind of parameters instead of just blindly replicating this node tree. Otherwise, you will have a kind of a painful moment, because there are so many parameters that you have to manually change by yourself, like increase the scale or decrease the scale, or increase the roughness or decrease the roughness, and so on and so forth. You have to tweak these values by yourself with your understanding and knowledge. Right now, the intersection detection doesn't seem very necessary. So we are going to move on with a branching system, which I think will make the intersection detection needed. Okay. So talking about the branching system, we basically just create a new point on these existing curves. And then we're going to do the same with this append pointer to curves, so that we grow another extension, and they will move with basically the same logic as we defined before. So it's basically a reuse of node tree. It's just the first thing we need to do is to create a new point on the existing curve. The way to generate points on this curve is quite straightforward. It's like you are joining branches to the existing stack. So the answer is join geometry, which is very straightforward. And how do we get new points? We're basically going to select that from the existing curve and geometries. So we take a separate geometry. There are several requirements I want to set to generate our branches. One is that it must be the endpoint of these existing curves, because I do not want to generate branches randomly just anywhere along my spline. So it should grow just like kind of trees at this specific moment when it's at the end of our curve. And there's a node called endpoint selection, which is very straightforward. A common mistake people made is that they do not untick these start sides. Remember that we only need to grow on the end, not the start. Okay. If you tick these starts, then it will be a problem. So make that into a selection. There are also other criteria or selection we need to make. So we need to make a Boolean AND math to turn on other probability. So another thing I would like to do here is that I do not want to grow a branch for every of these kind of points. I want to just randomly select some of it. So these points should not grow, that point should grow, that point should not grow, this point should grow, and so on and so forth. Okay. And the way we are going to do that procedurally is just to use a random Boolean, random value actually. And instead the float, we go with Boolean, so that there is a probability that 50% will be yes, 50% will be no. So we put that in. Right now, if you output this selection to join geometry, you will find that there will be no new branches. You will not see any new branches. And even if you increase the iterations, you will not see new branches. This is because these new points or new branches, they're using the same noise texture based on the same vector coordinates to generate the same decision, whether you're turning left, going straight forward, or turning right. So these new branches are overlapping with our geometry right now. So here I'm basically going to generate a different vector to hopefully give a different noise or decision for it to turn into other direction. And by default, this vector contains a kind of position attribute inside. If you put this position attribute inside, you will find that there is no any difference because it's internally built in. But in this case, we are going to take a vector seed. This is equivalent to just a vector mass. It's just more explicit. Instead of using this kind of vector, I'm going to use a integer seed. If you put that in, you will see some difference, but there's no new branches because you're still using the same seed for all these kind of branches. So the way we are going to generate a new seed for these kind of branches is that we are going to give them a kind of ID. So the idea here is that I'm going to store a named attribute for each new branches. And you can name whatever you want. You can name that as a generation, you can name that as an ID, or I'm going to name that as an H, which stands for hierarchy. And this is an integer value that you just set. And imagine our main branch is starting from 0. The hierarchy for our branches will be 1. And the next time, if the new branches is giving another branches, then the hierarchy will be 2. So the way to construct this relationship is basically we start with a hierarchy. Whether this is 0, or this is 1, or this is 2. And then each time when we are giving a split, we plus 1. Actually, instead of using this kind of math, it might be even better if you use an integer math node. It's not giving a strong difference in this case, but anyway. Okay. And now we are going to use this hierarchy, putting that into an integer seed. Then you will immediately see there are lots of branches being made out because they stood out from the original overlapping position. And here I do not need all these kind of new branches. Let's just decrease the probability, maybe to 0.1. And I'm also going to change the probability for each iterations. So I need a concept of loop index. I talked about loop index in the older tutorial. The idea is basically you start with the first loop, second loop, third loop, fourth loop, fifth loop, and so on and so forth. Okay, and this concept has been built in Blender since 4.3, I guess, and it's actually called iteration. I know it's kind of very confusing about these two terms, but I'm not the person who made this decision. But if you just look into the tooltips, it will mention this is an index of the current iteration. So I'm just going to put these iterations into the seed. Then you will having a different seed. This is not a very prominent, but it becomes very important when you're making other conditions. There is one more thing that I like to do with this loop index and our branches. Right now, we're changing this noise texture seed to hopefully make sure that our new branches is not following the same decision to turn left or straight forward or right. But we only have this many possibilities, and it's still very possible that they overlap because there are like a 33% of chance that they made the same decision, even with different seed. So I'm going to make a switch or condition to make sure that there is 0% chance they overlap. Now the way I'm going to do that is that I'm going to set up a turn for these new branches, so that no matter what you are going to turn if you are newly created. And if you turn, you must not overlap. And here we just set up a kind of switch. And then we switch with the vector. So if you're a new branch, then you will rotate. Otherwise, you will stay with the same direction. So how can we make sure about this condition system? How can we determine if this is a new branch? Think about our hierarchy system, that we start from 0, and for a new branch being generated, we put a +1 onto it. And our loop index actually also comes from 0. So we start from first loop, which is 0, and now we have a +1 hierarchy branch being generated. So in this case, you can see a kind of relationship that's an iteration +1 will equal to the hierarchy number for our branches. And in fact, you should put these values into an integer. It will not make a huge difference, but it is a good practice to do. So now we have this condition being made. You just output that into the switch. Right now, you will not see any difference because we haven't decided with this vector rotate. Just imagine if you just tweak with this value, and you can see there is actually a new branches coming out here, because it was initially making the same decision somehow, but now we're actively turning it in a different way. Next, we just need to generate kind of random value and the conditions to determine if it's going to the left or right. Of course, we do not allow it to go into the straightforward direction, otherwise it will cause the overlap again. So here I'm just going to use a random value node again, put that into the boolean, take a switch. I'm going to switch with the float, using the 2 radians so that I can input the degrees of false and true. I'm going to use a negative so that I can output a positive value and a negative value accordingly. And then put that into 45 degrees. Then you can see the 2 positions, they are nicely separated in this case with our extra turn. Unfortunately, it goes back to an overlapping position later, but it's fine because we are going to do the intersection detection anyway. Before we go into the intersection detection, I want to remind you about this random value node, which also contains kind of a seed, and you probably want to have a difference as well with this iteration. So you can put that into the seed, but here I want to remind you that you have a two random value using the same seed. So I often talk about these kind of issues in this kind of loop, whether this is a repeated zone or for each loop, whatever. So here you can use an index seed node that you input an index. We have our index, and you generate a different seed. And now you can just replace it. The good part of this preset is that it also gives you some extra options that you can just change the seed and the difference, and so on and so forth. Okay. Next, we need to deal with the intersection connection, which is kind of very straightforward. Knowing that we all start at this kind of a single point, and even if we are making a kind of new branches, we are starting with a single point, and we're basically extruding all these kind of curves step by step. And the entire concept of intersection detection in this case is that we're going to do a forward detection using RayCast. That if you shoot a ray to its forward direction based on this offset, and if you hit another curve, then you should stop moving. So this offset should be 0. And this is the logic of our intersection detection. To implement this function, we need to start with the endpoints. And this is basically the same concept as before. We start with this separate geometry, and we use endpoint selection. Make sure and check these start sides, and we're going to sample the decision for our points by index to each of our curves. So instead of points, it must be a spline or curve, and put that into the offset. Immediately you will see there is no change in the viewport. Otherwise, you are having a kind of error. If you do not capture that, you are having an error. If you're using the points, you're having an error. So it must be on a correct domain. Blender is going to rename this spline into curve. So if you do not find the spline in your list, try to look for curve. Or you just try one of them, and there must be one which is working in this case. Okay. Now we can start to work with our actual intersection detection process using this RayCast. Here I'm going to use a switch node to help with our decision-making process, and I'm going to set that to vector. So if we know this point is going to hit some other curves, then it should stop moving. Otherwise, it should stay with its original decision of moving. Right now, we do not have any change in the viewport because we haven't done anything with our actual RayCast yet. There's an issue with the RayCast that it does not support the curve. So if you input a curve line, you can see it outputs a kind of warning saying that input geometry has unsupported type curve. So we're going to make this curve into something else. So the RayCast is usually made for this kind of mesh geometry. So we just take kind of curve to mesh. And in this case, I'm going to use a bevel curve so that it becomes a tube-like structure. I do not need such kind of a stick tube, so I'm just going to take a value position and make that very thin. something like that. Then right now we do not see it, but it does present. And now if we can replace this mesh to the target geometry, then there is no warning. And then we can replace this curved line with our existing circuitry board for it to sample. And immediately you will have a issue with the viewport. This is because right now we're shooting a ray downwards at 0, 0, -1 direction. So imagine that you're forming a kind of tube-like structure and you're having a point to sample the collision. A ray downwards means that it will hit itself. That's why all these kind of tube points are giving a kind of collision result to stop move. In this case, we're going to replace the redirection with our forward direction. So now you can see we recovered a circuitry board, and you can actually compare the result with or without this kind of collision detection mechanism. Right now, there are two kinds of issues within our setup. The first issue is that despite improvements, you will see that there are still some intersection happening in our setup. This is a limitation with our setup. If you turn down the iteration and try to look how it actually happens, then you realize that the logic of our forward detection is that we start with the endpoint and shoot a ray in the direction of its movement. Then we find that there is nothing. Then it will make a decision of moving. And this is equally true for that point. It shoots a ray and it finds nothing. So it makes a decision of moving forward. But the reality is that both of them move forwards and then they accidentally intersect. So this is a limitation for our method. There are definitely ways to solve that, but it will be complicated to implement in this case. So I'm just going to forget about that. The other issue is something that we can improve in our setup. Right now, we are shooting a ray about 100 meters. And which means that from this point, it will shoot a ray and it finds a collision, then it will stop moving. But there is actually a lot of rooms that it's allowed to move. So in this case, we can limit the ray length so that we can minimize a kind of a premature death for our extrusion. So in this case, we can take the length of our vector. And yeah, in the range of our movement, there will be no collision, then it should go as well. So we put that in. Then you can see it move forwards a little bit. So this is kind of improvement, and you can increase more iterations. And hopefully you will find that there are more points being generated because less detections they see themselves in this case. There is another improvement we can make for this setup. It may not be very obvious at the first place, but if you think about the mechanics we are doing here, we are trying to append a point to curves. And if you think about that, even the offset is 0, we're still appending a new point at the end, a new point at the end, a new point at the end. This means that there can be many more points than what you are seeing in the viewport, and it will lag our computer and the node tree in this case. So the thing we are going to do is quite simple. That if we are not going to propagate, if the length is 0, then we should not propagate. If this length is greater than 0, then we should append a new point to these curves. So now if you put that into the selection, you can see there is a kind of change of the result. But more importantly, that we go from 170 back to 110. So there is a kind of improvement in performance because we remove all these kind of duplicate of points. The viewport shifts because different points will lead to different all these kind of index or hierarchy or whatever decision during this process. But essentially, this is kind of an improvement of our setup because it speeds up. For a circuitry board, this is basically finished. Next, we can discuss briefly about materials for this setup. I didn't discuss this in the older tutorial because this is kind of basic, and I've discussed similar kind of concepts in other tutorials repeatedly. So it's not really realistic to keep mentioning this. But in this case, I will just do because people have so many questions about it. I'm going to start with the bevel curve, take the value position, just to make a kind of a thin tube-like kind of structure. If you do not like a tube, you can also make a quadrilateral custom profile to make a kind of height, like kind of, I don't know how to call that, but the rectangle shape, whatever stuff. Okay. And then we take a set of material. And I'm going to put that into an emission shader. People asked about how to get the starting animation pattern, this kind of whatever electricity going. It's kind of very straightforward. You just put a kind of a sine wave on these materials. You take the shader editor, and then there's a wave texture for this emission. And you will see some issues because it's okay on the left and the right, but it's not okay on the north and the south. This is because we need kind of UV map so that it does not only go on X, but also on other directions. So we store a UV map, and we take the UV map. Then you will encounter another issue that some parts are very dense, some parts are very loose. Because these UV are of different lengths. The UV is always normalized in the range of 0 to 1. So the long curve will have a stretched UV map, and the short curve will have a kind of concentrated UV map. So in this case, we'll just normalize the process using this kind of length multiplier. And people also ask how to animate that. Oh, come on, just animate this UV map. Then it will solve the problem. I'm also going to decrease these parameters. Then you animate that. And then there will be another problem that you can see they all start from kind of black. How can you offset this animation? This is also going to deal with the UV map. That you are going to have a different index to offset your UV map. So in this case, I'm just going to capture an attribute. The reason I'm capturing an attribute is because this attribute only exists for our curves. It's the spline index or curve index. To take this spline index, I'm going to offset on our UV map. Then immediately we'll have a kind of a shift all these kind of results. And if you want, you can also change it to seed, but whatever. If you want to animate these textures, you can either just keyframe that or just combine X, Y, Z to put a time info on the x-axis, then you're going to have an animations with it. There are so many things that you can potentially do. In fact, you do not necessarily use the repeat zone. The benefit of using repeat zone is that I can just take the iteration to animate the growth of it. But sometimes it can be very slow, and you can also use the simulation zone instead. You just need to bake the cache of animation. So the tutorial is basically finished here. This looks to be a very huge setup, but if you go through step by step and understanding the mechanism of it, then it's not really complicated, because I finished talking about the principle basically at the beginning of this entire tutorial. We basically have 5 main parts. We start curve points, we move it, we add the branches, we do the detection, and then we put everything into mesh and the materials. So about the 5 main parts. Another important thing is that this is a procedural setup, that there are unlimited possibilities that I'm not able to show in a limited time. All these kind of parameters and settings, different seeds for a setup. And if you understand the mechanics, you can always modify the setup into something completely different as well. For example, I'm just going to duplicate this node tree to make everything collide with itself using join geometry. And in this case, I'm just going to import the planes back to itself as a second collider. And then I'm just going to move that. You can see then there's another circuitry board, and it actually collides with our existing whatever stuff. And you can even duplicate that, move that to somewhere else, then you'll have another different board. There are lots of different possibilities, including we do not necessarily start with a quadrilateral. We can even start with a curved circle. Then it will be something completely different. So there are all sorts of things that you can potentially do it here, but it depends on your understanding. So anyway, I hope you enjoyed this video, and I hope this tutorial can last longer than it should. I hope you enjoyed this video. I'll probably see you next time. Bye bye.